Swayam Prabha. Digital India. Educated India.
Hello. Today we will talk about calculus of variations by looking at some problems which will serve as examples. We will not solve them today, we will only learn how to formulate calculus of variations problems in geometry. First we will look at geometry related problems and then we look at mechanics related problems. So, here is the outline of the lecture. First we will discuss the geometry problems where calculus of variations is convenient to pose those problems. There will be minimization, maximization there, but the unknowns will be functions, which is the characteristic of calculus of variations. And then we look at the role of calculus of variations both in mechanics and structural design optimization. And what we will learn today is once again talk about what kinds of problems belong to calculus of variations. We looked at a few historical problems in calculus of variations in the last lecture, such as the Brachistochrone problem and Fermat's problem for refraction and so forth. Today we will look at a number of other problems belonging to geometry and mechanics. That is what we will learn today. And we will also look at how we can formulate them as the calculus of variations problem, and look at the connection between mechanics and calculus of variations, historically how the field of mechanics evolved or co-evolved with calculus of variations, and then look at the connection between structural design optimization and calculus of variations. In all of this we will learn one thing, which is about a functional. We used that word in the last lecture also. Today we will look at a number of functionals so that we know how a functional looks like. So, in geometry there are a number of problems and all of them pertain to minimal or optimal curves and surfaces. In the case of minimal curves or optimal curves, we look at geodesics, something that we had talked about in the last lecture also, and the chain that hangs when you put it between 2 points under gravity, what shape does it take, that type of problems, and a number of problems where there are minimal surfaces such as what soap films do and a number of other things that we come across in geometry and mechanics. So, when it comes to mechanics and calculus of variations, there are something that we need to take note, and it is very important, and that is there are three ways to write equations of statics and dynamics, that is static equilibrium as well as dynamic equilibrium. And these are listed in the table here. Under statics we have something called force balance. We all know that when all forces acting on a body are balanced, and then the system will be at rest, what we call steady state or static equilibrium. And the corresponding thing in dynamics is F equal to ma, Newton's second law. This is how we normally learn mechanics in high school and undergraduate courses as well. But if you want to learn mechanics from an analytical viewpoint, then you will realize that there are two other ways which are equally independent as the force balance and Newton's second law, which will give you the same result, but by a different means, and those are principle of virtual work for statics and D'Alembert principle for dynamics. And similarly there is a third one, which is the principle of minimum potential energy for statics and Hamilton principle for dynamics. So, you can take any one of these three and derive the remaining two. So, you can belong to different school. The first school is force balance, Newton's second law, second school is principle of virtual work and D'Alembert principle, third school is principle of minimum potential energy and Hamilton's principle. So, all of these is what we should appreciate in the framework of calculus of variations, which you can see in the first column, where we have put this as calculus of variations, that basically gives you minimum potential energy principle and Hamilton principle, and then we put something called an intermediate result, and that actually leads to principle of virtual work and D'Alembert principle. And the third one is the final result, or rather where we write the differential equations, and that gives you force balance, and in the case of dynamics Newton's second law. So, all of this starts from calculus of variations. Okay. And when it comes to structural design or structural optimization, those problems are naturally calculus of variations problems, and when we look at the unknowns, it could be the shape of a particular surface or a boundary, or the topology of a structure, or the size profile variation of a structure, and so forth. Those are all the design variables or optimization variables. And what do we optimize for? All of those are listed here. When you think of a structure as a designer, you would be interested in stiffness, flexibility, strength, weight, cost, manufacturability, natural frequencies, mode shapes, stability such as buckling loads, and then contact stresses and things like that. For all of these things we can pose calculus of variations problems. First, let us look at geometry and calculus variations. In particular, let us look at minimal curves or optimal curves. Let us start with a very simple problem for which we all know the answer, and that is, if you have a plane where we have indicated the x axis and the y axis, and there are 2 points given. Let us call this point A and point P. Now, in a plane, you know that between 2 points, if you want to find a curve of least distance, the answer is the straight line joining the 2 points. But let us pose this as a calculus variation problem and then see how the objective function or the functional looks like. So, for that we take a small element such as the one that is shown here, call it ds, and enlarge that over here. So, the ds, and this is dx, this is dx, and this is dy. Okay. So, ds in that case is given by square root of dx square plus dy square. We take dx out and write it as square root of 1 plus dy by dx square, or in our notation we use y prime, it is a symbol for dy by dx. So, what we get is this length of the curve or the distance of the curve between points A and B. If you draw a curve like what we have shown the black here, the length of that is given as an integral, or what we call a functional, which is from limits x1 to x2 square root of 1 plus y prime square dx. So, this is called a functional. So, let us write that one more time. So, this is called not a function, functional. Okay. So, if we minimize this functional, that is L is given like a functional, in this case it looks like it is an integral. If minimize that with respect to y of x, because that is what we do not know, or at least we are pretending that we do not know. If minimize this function with respect to that function y of x, then we will get an equation whose solution will be a straight line, which we know as the answer here. Okay. That is the simplest calculus variation problem in geometry. So, we say this L with respect to y of x, and what is given here, the data, the two coordinates, x coordinate x1 x2 and y1 y2, that is this point and that point are given. You need to find that curve that has the least length, and that turns out to be a straight line. Anyway, we will look at solution much later. Let us first understand how these functionals look like. That should be our focus, because we will consider a number of problems to look at what a functional looks like and how to formulate it. Here formulation was quite easy, there are no constraint, you just minimize an integral x1 to x2 square root of 1 plus y prime square dx and no constraints. Now, instead of those 2 points being in a flat plane, if they are on a spherical surface such as what is shown here, then there are no straight lines on a sphere. That is what we had mentioned in the last lecture also, and hence we have to find a curve which is called a geodesic. Geodesic is a generic term, on any kind of surface you can find a geodesic. Now, let us look at how we formulate the geodesic problems. Okay. First, we have to express curves on a sphere in parametric form, meaning that when you are moving on a sphere you have 2 degrees of freedom, rather you need 2 coordinates. But now, when you are constrained to move on a curve, you have only one variable and that is our parameter. So, we express first the sphere as 2 parameters theta and phi and get x, y, z coordinates and find the differentials of those things. So, x equal to r cosine theta cosine phi, y equal to r cosine theta sin phi and z equal to r sin theta. So, here theta will be the elevation angle, phi will be azimuthal angle, meaning that if I take any point, let us say a point over here, let me change the color so that that blue and this blue do not mix. Okay. If I have a point there, if I project that point onto the xy plane, I look at this. So, this will be the angle phi that we are taking. First of all, we have this r from here to here, that distance will be r, and this angle will be theta, what we call elevation angle. Theta is elevation angle, as if the r that is here is risen up by rotating by an angle theta, then it goes there. Okay. So, this gives the length of this to be r cosine theta and this height, that is z coordinate, is r sin theta. So, from here to here is r sin theta, which is what we have written here, and then this portion will be r cosine theta, and then we have to get the x and y coordinates. So, we have to look at how much is this, how much is that, then they will be whatever cosine theta that we had already, and then I have to take cosine phi component, because the phi is the azimuthal angle, and sin phi for the y coordinate. That is how we wrote this x, y, z coordinates in terms of 2 parameters theta and phi to access or to denote any point on the spherical surface. Now, what we are interested is a curve with 1 degree of freedom to go along that. Before that, we are taking differentials of all these. So, dx that we have, theta and phi are variables, we differentiate with respect to them and get these 2 terms, and dy we get these 2 terms taking y equal to that, and z r sin theta simply becomes r cosine theta d theta, because it depends only on theta z coordinate, where x and y depend on theta and phi. Okay. Now, if I take any small segment on that curve, if I call that ds, the ds or square of that is given by sum of all these, Pythagoras theorem applied twice, and we substitute for dx, dy, dz from these things over here, then we get a long expression for this ds square, and when we simplify it, trigonometric identity is used, then we get ds square is r square plus times d theta square times cosine square theta d phi square. Okay, that is what we get as ds. So, the ds that we have here, this is ds square, ds will be square root of that r times all of this. Why do you need this? Because we are interested in finding a geodesic, that is a curve of least distance. So, we take this expression that we have for ds and then integrate it to get the total length of any curve that is there on the spherical surface. So, in order to get that length, we have to take this L and integrate it all along this curve. Okay. that basically means that you go from, if I take here d theta square plus cosine square theta d phi square, we divide by d theta and take it out, or rather d theta is taken out, that gives you 1 plus cosine square theta d phi by d theta square, okay, and this will be the length of the curve there. And now if you prescribe a curve on the sphere as a function of phi, which is in terms of theta, because we have two variables theta and phi to reach any point on the surface of the sphere. If I consider that phi is a function of theta, then I have only one degree of freedom to move, and that is theta. Okay. That is when you move along a curve, you only vary one variable, that if you take that as a theta, then phi will be a function of theta. So, that becomes our unknown function here. Then the integrand that we have here, cosine square d phi by d theta, we put that in and try to minimize this integral subject to basically what is given, that is theta 1, theta 2, phi 1 and phi 2, that is starting and end point are given. We need to find this function phi theta to get what is called a geodesic or minimum distance curve. Now, this geodesic actually can be drawn on any surface, any three dimensional surface. Here one is shown. So, if I take 2 points here and here, there will be one particular curve which basically follows the geodesic or rather minimal distance curve. And for a general one, we can write for that also. In this case, just like before, we had theta and phi, we have taken two parameters u v, because on a surface we have 2 degrees of freedom. Previously on a spherical surface we took theta and phi, now we have taken u v. So, x is a function of u and v, and so is y and so is z. So, now like before we take differentials dx dou x by dou u times du plus dou x by dou v times dv, likewise for y and z. Once you have these quantities, we can express that ds, the small distance that we want, as exactly like what we had before, square root of dx square plus dy square plus dz square, and substitute for dx dy dz using what we have derived here. Okay. If you do that, you get some p, q and r. If we are wondering what those are, this is how they look like: p equal to something, q equal to something and r equal to something. Okay. So, this is how we get this integral. Now, for finding the geodesic, we have to minimize this, that is basically ds in terms of p, q and r, which are known once you assume a parametric form for the surface. Okay. Then p and q and r are given as follows. This is what you do with respect to v as a function of u. Previously for a sphere we had considered phi as a function of theta. Here we consider v as a function of u, because you have 2 degrees of freedom, but you are constrained to move along a curve, then one of them has to be made independent, other has to be made dependent. Here we have chosen to make u independent and v dependent on it. We have to find v of u function, then we would know where the points on the geodesic will be. Okay. So far we did not have a constraint, now we will try to have a constraint. Okay. We look at the problems which are known as isoparametric problems, meaning that they have the same parameter. Okay. Now, the integral form that we had, we call it a functional. So, you know that if there is a functional as the objective function or in a constraint, we call it a functional. We will learn more about functionals later on. Okay. Here is a problem of calculus of variations, historic problem, where a constraint is also involved. A constraint is that the length of the curve, if you are given a piece of string, you need to arrange it on a plane in some fashion, so that the area enclosed by it is maximum. Okay. This is a classic problem called isoparametric problem or Quinn-Diros problem, but how do you do that? And the answer for this is actually a circle, but we will learn how to pose it as a calculus variation problem first. So, in this case area enclosed by a curve, which is what you see in this green one, is given mathematically in this fashion. Okay. If I take x and t as functions of a parameter t, x and y as a function of parameter t, then the area enclosed by a curve, if you give parametric form for the boundary, area enclosed is given by this particular integral. Okay. Perimeter on the other hand is given by this particular integral. Okay. That is something to remember when you have them. Then we can pose a problem to maximize the area. You notice that I put minimize negative area, negative a, that is same as maximizing the area, and what we are controlling or optimizing with respect to are these two parametric equations that define the surface x of t and y of t, subject to of course the length constraint, because that is given, only a piece of length, known length string is given to us. We have to find x t y t such that area is maximized. This problem is kind of geometry and mechanics, it is a combination of the two. This is if I take a chain between 2 points, let us say here the hand should move a little bit there. So, you are holding the chain between 2 points, it takes a particular shape, and that shape how do you find? Make that the unknown. So, the shape of the chain is unknown, and what do we do here? We minimize the potential energy. So, P E here is the potential energy, it is the energy of the system by virtue of its position. In this case there is gravity field. So, the potential energy basically comes from gravitational energy, and that is rho g y square root of 1 plus y prime square dx, that is square root of 1 plus y prime square comes because we are starting with ds, which is dx square plus dy square under square root, take dx out, then you get 1 plus dy by dx square, which we denote as y prime. Okay. And here also we have a constraint that length of this chain is fixed to L, and that is what we need to do that. Again we will do the solutions later on. First recognize how a functional looks like, whether it is an objective function or a constraint. Here is a problem, it is a geometry problem which I call Chatterjee problem, because Professor Anindya Chatterjee, who is IIT Kanpur now, he had discussed this and in a way posed this problem. And here imagine that a farmer has to take some land enclosed by 3 roads. Though here is road 1, let me go back, let me change the color, yeah. Let us say okay, this is pen. Okay, here is road 1 and road 2 and road 3. 3 roads are there. So, here is 1, here is 2, 3. Okay. The farmer can choose the land as shown here, and this is the curve that we have y of x that he can choose, but there is a river. So, he cannot have the land that is going to penetrate into the river, he has to choose it below the river, that is a constraint which is an inequality constraint like it is shown here. Again I have to change the color of the ink. Let us choose farmer, so we will choose green color. So, that is constraint says that y of x has to be below r of x, r of x defines the curve of the river. Okay. And what does the farmer want to do? He wants to maximize the area enclosed, that is what is seen here, that has to be maximized. To put minimize minus a, our convention is to write all problems as minimization problems. So, when you want to maximize it, we say minimize minus of that area with respect to y of x, that is what he has to choose to put a fence there, and he wants to enclose maximum area, and the length of the fence, because the budget constraints, the farmer fixes, it should be L. Okay. Now, how do you solve the problem? Because you have a functional here and there is a constraint which is also a functional, and there is a function constraint on y that should be less than or equal to r of x, which is the river curve. This is how we formulate the problem based on what we have. Later on we will discuss how to solve these things. So, now let us we discussed a few problems involving curves. Now let us move to surfaces. So, this is a problem similar to what Newton had considered to get the surface of revolution for a body to minimize the drag on it. But in this case we are looking at a problem which is not to minimize the drag, but to get this surface in a way that it is minimized. You are given a shape that you have to find this shape, which is our function, this y of x. We are given a certain length, which is this L. We want to minimize between 2 points. Let us say a point is given here and here. We would like to find a curve that minimizes this surface of revolution for this. Okay. So, for this we have this functional, which is 2 pi y, because surface of revolution, if I take a perimeter like this and length of that if I take anywhere, that is ds, and y, which is the height there, 2 pi y into ds, then I would like to extremize this surface area subject to this constraint, which is given length, okay, between two given points, the minimum surface. And for that we get a problem such as the one shown here. Okay. Here we are taking a y, a curve, and then we are getting minimum surface with that. So, it is not really a surface related problem, it is more like a curve, which is a surface of revolution is going to come out of that curve when you revolve it around this axis. Okay. It is a transition between curves and surfaces. If you want to look at a truly surface problem where the surface are unknown, we have to look at soap films. If you take a wire and put it into any 3-dimensional shape, dip it into soap water and take it out, soap film like it is shown here will take a strange shape. Strange shape is actually a minimal surface. So, soap film has to adhere to the boundaries of the wire where soap film has to attach, but in between it tries to minimize the surface energy and actually surface itself, right. It is a very least surface area kind of surface will attach to the boundary of this. It is a very interesting experiment to do, one can do it at home very easily. Take some soap water, take a wire, putting into 3-dimensional shape, dip it, it will just come. So, there could be lot of interesting shapes such as the one that is shown here. So, you have to just take a wire, bend it whichever way and dip it, you will get the minimal surface. So, soap films do this minimal surfaces very efficiently. Okay. How do you pose that problem? Here we have to minimize the surface, and that is given as a functional here, again an integral. Now, if you notice we are integrating over a domain. The domain is if I take a projection of this surface onto xy plane. So, this is our domain, which is denoted as D here. Okay. So, on that we have to get a surface, that area of that surface, that is area of this surface, is given by this expression. Again this will be dx square plus we have dy square and a dz square. So, it is basically a little geometry will involve to get this square root of 1 plus dou z by dou x square plus dou z by dou y square. You are integrating with respect to two variables x and y over the domain, that is a projection of that surface. So, now you realize that a functional need not be involving only one variable, you can just x. Now, here we have x and y. Okay. So, look at the functionals as we go along this. And this is actually very important problem. If you take a helical helix like this, a wire, and dip it, that also forms a minimal surface. Just about anything, you take complex shape like this and dip it, it will get you this. It is a very important problem. In fact, one of the people who has solved it was awarded Fields Medal, which is the highest prize that can be one can get in mathematics, like a Nobel Prize equivalent. That was awarded to somebody who looked at this problem for irregular shapes such as this. You take a wire and put it whatever shape you want, finally if you were to solve, you get a minimal surface, which has lot of implications in mechanics as well as geometry is a very important problem. And in optimal control as well, there are lot of calculus variation problems, and one of them is given here. Let us say a helicopter has to circle around to, let us say, surveillance purpose an area. The speed of the helicopter is, let us say, fixed. What is the variable is the alpha, the steering angle. The speed is fixed. So, if you want to make a closed curve, you have to change your steering. If you are the pilot of the helicopter, then you would be rotating and change the direction. For that, if you want to maximize the area enclosed by this closed curve as you are circling in air, that functional takes this unusual form. So, here the unknown is alpha as a function of t, which is the steering angle. This is the steering angle, that becomes your variable. The area, again we want to maximize that area. So, we have minimize negative of area. That area expression is like this. So, there is sin alpha t, cosine alpha t, and there is an integral within this bigger integral. There is one integral here, right, overall. Within that there is another integral. So, and then one more here. So, a functional can take many different forms. Here is a very complicated form, there is integral inside an integral. We saw integral on one variable, integral in two variables, and then now an integral which has an integral inside it. So, we will study the notion of a functional as we go along and take a number of problems. We will take we will end this here and continue with mechanics later. Thank you.